All right, hi everybody. Welcome to section 2.1, start of chapter 2, and this is going to be the derivative chapter. So we were a little introduced to derivatives in last section's material 1.6 with the definition of derivative, instantaneous rate of change, and now here we get into the real uh, topic of it, and we're going to be using for the rest of this class in terms of derivatives, right? These kind of rules and um, tricks and tools, right? So section 2.1, derivative of a function and its two interpretations. Okay, so at the end of today's lesson, we will be able to know what it means to find a derivative. Key big word, derivative. Recognize different derivative notations. Use shortcuts and rules to find common derivatives. That's going to be important. It's going to save us a lot of time. Interpret the meaning of a derivative for any function. And what we're going to learn is find the equation of a tangent line to a curve at any point x. So last class we were, you know, learning the notion of a tangent line, what it means, instantaneous, and we can use derivatives now in our tools that we're going to learn to be able to find that equation of a tangent line. So in last section, right, we learned about that definition, that limit definition about instantaneous rate of change by using this limit, right? We use a limit. We also like found average rate of change around intervals. But this is a limit that occurs so many times in business, science, engineering. When we calculate rates of change, we give it a special name called the derivative, right? So the derivative of a function denoted f prime of x, this is read as f prime of x. So if you hear me say that, that's what I mean, the derivative. So denoted f prime of x is given by limit as h goes to zero of the same type of definition of f of x plus h minus f of x all over h. But, this is more like in general now, not like at a specific point. This is more like in general of a function. So say like in general. So there are two ways to interpret the derivative f prime of x, and that is, instantaneous rate of change or the slope of a tangent line, which is both things we covered last section where we're just finding the slope of that tangent line, meaning the instantaneous rate of change. So that's the way the derivative is kind of interpreted. So here's some other annotation for this, right? They all mean the same thing. Right? They all mean the same thing. Uh, so don't be too scared by it. But we really will only check out these main three, where it says f prime of x or it says y prime, right? That's how you say the middle one. And this is like dy over dx. Uh, we rarely use it. You might see it in an example or two, but you know, there's also another way here where it's like says dy dx, and you have this little x minus a right here. That just means like derivative evaluated at a. That's kind of what that means. But anyways, let's get into it a little bit. So here's our first rule, right? Derivative of a constant function. So if I want to find the derivative of c, right, where c is just a constant, right? So if I want to find the derivative of any constant, it's just a number, there's no variable, right? No variable attached. But if I want to find the derivative of that, what that will always be is just zero. Derivative of a constant is just zero. So for an example, right? Let's say I have my function is like two, right? And I want to find the derivative of that. Well, two is just a constant. So this guy just becomes zero. My derivative is just zero. Okay, so don't overthink it. It's just derivative of a constant is zero. And that makes sense because if you think about a slope, right, of a line, I'm sorry, slope of 2, well, this has no slope. It's just a horizontal line. So that's why the derivative is 0, because there's no slope. But okay, let's keep moving forward to power rule. That's the big one. That's one we use mainly all the time. So what is the slope of a line y equals x, right? If we think about a slope of y equals x, right, it's just we have that slope right there, right? Y equals mx plus b. And so if our function is y equals x, well, we have that like invisible 1 right there, right? So that means our slope equals 1. So the derivative of x is really just 1, right? So in general, the power rule, what does that mean? So if n is any real number, then the derivative of some x to the n, right? It could be like x squared, x to the fifth, x to the 10th, something like that, right? What the power rule is the derivative would be n times x to the n minus 1. That's the power rule. The n drops down and we subtract 1 from it. Okay. So this also relates to x, right? The derivative of just x. Because think about it. If we have y equals x, right? That's the same thing as like y equals x to the first power, right? What am I going to do? Well, if I take the derivative, I'm dropping this down and I'm subtracting 1 from it, right? So that means y prime equals x to the 0, and anything raised to 0 is just going to be 1. So that's how the power rule works. Okay. And this happens with any type of like exponent. So let's look at some examples. So we have example when we want to find the derivative of each one of these functions. So we have f of x equals x to the third, right? So if we want to find the derivative of this, what happens is this 3 drops down, and I subtract 1 from 3. So this becomes 3x squared. And that's it. That's my answer. Okay. So part B, f of x equals 1 over x to the fourth. So remember, we want to use our power rule, right? So say want to use power rule. Okay, want to use power rule, but the issue with the power rule is that it needs to be, a numerator needs to be up top. So what do I need to do? Well, what I need to do is bring this guy up to the numerator. And that's just some exponent uh, properties that if I bring this guy up, it's going to be x to the negative 4, but I'm allowed to bring it up. So what I'm going to do is bring that guy up so I can use a power rule. So this becomes this becomes x to the negative fourth now because I brought that exponent up, just exponent properties. And now I can use a power rule. So power rule, once again, I'm bringing that guy down and I'm subtracting 1 from negative 4. Be careful with subtracting it, not adding it. You're subtracting it, so it's going to be a bigger negative number. So that means f prime of x is going to equal negative 4 x to the negative 5. Okay. And just to clean this up, right, it's just cleaner to have positive exponents. So what I want to do is make this x to the negative fifth positive. So what I can do is just bring it back down and make that positive. So what this becomes is negative 4 over x to the fifth, right? What I did was just bring that guy down to the bottom. And that's my answer. Okay, so last one, we have f of x equals x cubed to the four with the fourth root. So kind of recall from the algebra review, that if I have something like x to the a, and then it's like with the b root, right? I can rewrite this as a fraction with the power with the fraction, right? So this could be like x to the a over b. It's the same exact thing, right? Think about like a square root. So you have like square root, right? That's like saying x to the 1/2, right? So that's kind of how we go about this. So I want to rewrite this in this form so that I can use the power rule because I can't use the power rule like this. So what this becomes is x to the 3/4. Okay, and so now I can use the power rule. So power rule, that guy goes down, I subtract 1. So my f prime of x is 3/4 x to the 3/4 minus 1, which is -1/4. Okay, so once again, we kind of like positive exponents. So what I want to do is bring that guy down, move that guy down. So I'm going to move that guy down and make it positive. And what I get is 3. I get 3/4 x to the 1/4. Okay, so that's it for this video. We'll move forward with the next one. Thank you. See you next time.